Okay, welcome back. Part B of this first section, 1.2. So let's recall. If you had a position function, some projectile, vehicle, spaceship, whatever it is, with a position function, what you could do is, given some time, you would be able to relay the position of that object, right? You would be able to say where it is as long as at some given time. Now, a velocity function, of course, would be the information you would be able to express. It would be that particle's velocity at some point in time. Now, it should make sense that if you start with a velocity function, right? So if you're driving somewhere and I have access to your car's velocity function, that would mean that I could, in essence, at any point, plug in a time and figure out the rate of how fast you're moving. However, that doesn't mean that I'm going to be able to predict where you were or where you're going to be. Think about that for a second. I mean, yeah, you can take the derivative of position to get to velocity. And yes, you can integrate velocity to get back to position. But as soon as you integrate velocity to get back to position, you have, remember that constant of integration, you have that plus c. And now that plus c, that constant of integration, means that there is an infinite amount of possible position functions, right? More to the point of what I was saying. So just because I know how fast you're going doesn't mean I would be able to know where you'll be in an hour, because I don't even know where you are now. So how would I know where you'll be in an hour just because I know how fast you're moving? Now, in differential equations, when you're finding solutions to differential equations, many times the solutions are what we refer to as general solutions. It is a family of solutions, right? One of an infinite amount of solutions. Now, of those infinite solutions, there is the true solution, right? The one solution, the actual, or what we call the particular solution, right? So if I knew where you started and the direction you were traveling and I had access to your speed, then I could predict your position. But notice I need more information. I can't just have your velocity. I need to have, your velocity as well as, say, a starting point or some additional information. So what we want to do is, this is what we call initial value problems. And the initial value problems, we're going to see if we can move from general solution to particular solution. And the only way to move from general to particular solution is if they give us more information. So take a look at example 6. So we want to show that this function is a solution to the following differential equation, right? But more importantly, we want to show that sine of x minus cosine of x is a solution to this differential equation given these initial points, right? This initial information. So whenever you are solving an initial value problem, right? Notice that in the previous examples we weren't given this extra information. So just to make sure you understand, y of 0 is equal to -1. The way you would, obviously, the way you would translate that is that this is just a point, right? It's basically saying when x is 0, y is -1. This is another point, only this is a point on your derivative. Again, when x is 0, y is 1. So what we want is, so again, let's just, using our example with you driving, if this is your velocity, let's assume that I was able to get back to a position function. Now, this alone won't help me figure out where you'll be in an hour. But if I have this position function, as well as some additional information about where you started, etc., then I can get a particular solution, a true position function that would be able to predict where you'll be in an hour. So we want to show that the following sine of x minus cosine of x is a solution to the following initial value problem. And let's go ahead and go to the next page. So what I've done is, with this differential equation, I went ahead and wrote it using y notation. I do that when we have, second order differential equations, right? Like second derivatives, because this y double prime is just much easier to write than this Leibniz notation for second derivatives. But nevertheless, this is the differential equation, and we want to show that this is a solution, to this differential equation. And then we want to go a little bit farther and show that no, this is actually the solution to the differential equation given these initial points of information. So I've taken the liberty of, so here is our proposed solution, right? Sine of x minus cosine of x. And you know what we're going to have to do. We're going to have to plug information into our differential equation. So I've taken the liberty of taking the first and the second derivative. And what I'm going to do is I'm going to plug in for my second derivative and also plug in for y. And let's see if we have a solution, right? Forget about a particular solution. Let's just figure out if we even have a general solution. So we're gonna sub this information in to our solution, or I should say proposed solution. And let's see what happens. Well, I have negative sine of x plus cosine of x plus sine of x minus cosine of x, and that should equal 0. And you can see that if you drop these parentheses, sine cancels sine, cosine cancels cosine. So you do end up with a statement, a true statement. And this is true, right? This is true for all x from, that's just element, from negative infinity to infinity. All right, so all that's true for all x from negative infinity to positive infinity. So what do we know right now? We know that we now know that this is a general solution. So now let's see if we can go from general solution to particular solution. So let's go ahead and write these initial values, right? So we have y of 0 is equal to -1, and we have dy dx of 0 is equal to 1. So again, this is a point on your original curve, and this is a point on the curve of your derivative. So 0, -1 should be a point on your curve, and 0, 1 should be a point on your derivative. So let's just imagine, if you will, let's just imagine that this is where you started when you're driving at this position. So if I come up with a position, a position function, and if this position function doesn't go through this point, then there's something wrong, right? Because if you started here and I have the true position function, then I should know, I should be able to that point should be on this curve, right? Likewise with my a point on my derivative. So all that we need to show is we need to show that this is a point on your original curve, and we need to show that this is a point on your derivative. So let's go ahead and jump in. So what I'm going to be doing, let's start with f of 0 is equal to -1. Right? Let's start with this point here. So that means when I plug, here it is. So when I plug 0 in for x, and I should be getting -1. So f of 0 is equal to -1. So let's go ahead and I'll write the original f of x first, and then I'll plug in. F of x is equal to sine of x minus cosine of x. While I'm here, and I'm going to be doing the next point as well, so I might as well go ahead and write f prime of 0 is equal to +1. And I may as well go ahead and write the first derivative, I'm sorry, here as well. So that's cosine of x plus sine of x. Okay, you ready? So let's plug in. So we're going to be plugging 0 in for x, and we're going to be plugging -1 in for y. So we're going to be setting it equal to -1, and we're going to be plugging 0 in for x. So -1 is equal to sine of 0 minus cosine of 0. Well, that's just -1 is equal to 0 minus 1, or what? That's just -1 equals -1. So that point works. Now let's do the same thing with the derivative. So I'll be setting the derivative equal to 1, and I will be plugging 0 in for x. So now I have 1 is equal to cosine of 0 plus sine of 0, or 1 equals 1 plus 0, 1 equals 1. Again, so we started off this first round of subbing, told us that we had a solution. Maybe not the solution, but we have a solution, okay? A general solution. One of an infinite amount, but we have one of them. Once I checked my initial bounds, I now know that I have the solution, right? The particular solution to that differential equation. Hopefully that helps. So example 7, we're going to go through this fairly quickly because we've already done a lot of the legwork for example 7, because this is going to call upon the work we did in example 2. So if you want to pause the video and grab the work we did from example 2. But if you recall example 2, we wanted to show that this is a solution to the differential equation. We were able to show no matter what you choose for C1 or C2. But now the question is, if this, given this initial information, what must we choose for our C1 and C2 such that these initial points hold? Right, so the goal is to be able to make a statement C sub 1 equals, C sub 2 equals, must equal, and whatever these, so we need to find out what these must equal so that this is a solution that goes through these points, right? Okay. Well, just like prior, I'll go ahead and write it. So I have, y of 0 is equal to 2, right? So that's just the point 0, 2. And I also have dy of dx of 0 is equal to negative 3. So 0, negative 3. Okay, so how do we do this? Well, let's go ahead and, so here's our original function. Let's go ahead and we're going to set f of x equal to 2, and we're going to plug 0 in for x. So we have 2 is equal to c sub 1 e to the negative 0 plus c sub 2 e to the 2 times 0. All right, let's do the same thing here with our derivative. So we're going to be setting our f prime equal to negative 3, and we're going to be plugging 0 in for x. So now we have negative 3 is equal to negative c sub 1 e to the negative 0 plus 2 c sub 2 e to the 2 times 0. And now what you're seeing is a system of linear equations. So this system, let's go ahead and rewrite this. We have 2 equals c sub 1. Now e to the anything to the power of 0 is 1. So that's just c sub 1 times 1 plus c sub 2, again, 2 times 0 is 0, e to the 0 is 1. Now, here we have negative 3, and that's going to be negative c sub 1. And again, if e to the 0 is 1, it's just 2 times c sub 2 times 1. So plus 2 c sub 2. Okay, and there you have. So this is just a system of linear equations. All right, remember substitution method, elimination method. Remember, if you had me for linear algebra, remember REF, reduce row echelon form. You can use a matrix to solve this, whatever you'd like. But what we end up with is, we can do this by hand. So if we just add them, we have negative 1 is equal to, well, the c sub 1's cancel, is equal to 3 c sub 2. Therefore, c sub 2 is equal to negative 1/3. So I now know that c sub 2 is equal to negative 1/3. Okay, and you already know the deal. Once you know, remember for substitution method, elimination method, once you know x, you plug it back in for y. Once you know y, you plug it back in for x. So now that I know what c sub 2 is, if I plug it back in, I should be able to solve for c sub 1. So 2c sub 1 plus c sub 2. Let's plug in for c sub 2. So that's I don't know what I just wrote. Let me try writing that again. So 2 equals c sub 1 plus c sub 2. Plugging in for c sub 2. So that gives me 2 equals c sub 1 minus 1/3. Solving for c sub 1, we get c sub 1 is equal to 7/3. And there you go. So if you want a solution to this differential equation that also goes through these points, then you would need to choose 7/3 and -1/3 for your C values. Okay, so a little bit about, let me say a little bit about implicit versus explicit solutions. So my experience has been that students grasp explicit solutions fairly well, but then implicit solutions can sometimes, maybe it's the language that I use or something, but they have a little bit more trouble with that. All I want you to know is henceforward, it doesn't matter, I'm just going to refer to implicit or explicit, it's just a solution, right? So when I say a solution to a differential equation, it could be implicit or explicit. So the next thing I want to show you, next thing we want to go over is the first real theorem we get to in differential equations. And it's the idea of existence and uniqueness of a solution. So look, if you're going to solve an initial value problem, right? If you're going to solve something like this, or if you're going to solve something like this, like we did in 6 and 7, well, there's two real pieces of information that you want to know, right? If you're going to solve one of these differential equations, obviously you want to know there is a solution. And the second thing you want to know is that that solution is unique, right? It is unique in that there's no other solutions. Well, the way this theorem works is it guarantees us, right? So we're gonna go over the criteria, but if the criteria is met, then this theorem guarantees that not only do we have a solution to our differential equation, but that the solution is unique. And I'll try my best to go through the theorem with you, but the way it works is we'll just assume that here's some differential equation and some initial value problem. Right, so we got some differential equation and some initial value. Now, the first thing, if both your function and the partial of that function with respect to y, if these two are continuous functions in some rectangle. Right, so to make sure you understand, so here's some curve. Now when you would integrate and get plus c, this is one of the possibilities. Here would be another one and another one. Do you see how, depending on the c value, you have an infinite amount of solutions? Now, we want to be guaranteed there is a solution, and we want to be guaranteed that whatever that solution is, it is one of a kind. It is unique. So the way you want to think about this is, so here is that initial point, right? Like that would be this point right here. Now, of all those curves that I drew, only one of those curves goes through this initial point. Right? The rest of them are just vertical translations. Remember, if I knew you were located, at your house at this time, I know this one piece of information about your position function, along with your velocity. So we have to be guaranteed continuity. And then not continuity throughout the entirety of the domain, but throughout some rectangle that contains that initial point, right? So do you see how this rectangle contains that initial point that we were given? Has to be continuous through that rectangle, through that interval, through that rectangle. Okay. So as long as we have this criteria, then the initial value problem has a unique solution. And I will not get into the the formal aspect of this. I think it's fairly intuitive that if you have a bunch of if you have a general solution, then you have one of infinite. But you have a particular solution, it's the one curve that goes through that point that you were initially given. So how do we use this existence theorem, right? So let's take a look at example 8. And here's what we want to do. So for the following initial value problem, the question is, does theorem 1 imply the existence of a unique solution? Okay. So we got 3, I'll go ahead and write it as 3y prime is equal to x squared minus xy cubed. And along with that, we have y of 1 is equal to 6, right? In other words, 1, 6. Okay. So let's get back to the theorem. So the first thing the theorem says, we have to be assured that f and the partial of f with respect to y is continuous. So let's start with f. So let's take our differential equation and let's solve that for dy dx. So let me go ahead and do that over here. So we want to get dy dx by itself. So divide by 3. Divide by 3. That gives me y prime is equal to x squared minus xy cubed over 3. Now, is this continuous? Is this a continuous function? Well, it is, right? It's there's no vertical asymptotes, there's no jumps, holes. So f is continuous. Let's take a look at the partial of f with respect to y. So now we're taking the partial of f with respect to y. So let's go ahead and, since this is my derivative, let me go ahead and rewrite this down here. Instead of having divide by 3, let's just have 1/3 of x squared minus xy cubed. I'll say a couple things about partial derivatives in just a second. What we need to do now is we're going to need to how do I put it? We're going to need to take the partial. So, okay. So partial derivatives is a topic in Calculus 3. And I do realize that it is a possibility that you are in my class right now and you have not taken Calculus 3. Now, there's not a lot in Calc 3 that you need to have for differential equations, but you do need to know how to do partial derivatives. You can look up some videos, you can email me, I can get you some videos on partial derivatives, but this is one skill that you need for differential equations, is how to do partials. So, but really what we're going to do is, since it's been a while for, I'm sure for many of you, we're going to take the derivative of this, we're going to, with respect to y, but we're going to treat x as if it were a constant. Right, so that's going to be 1/3. So let's think about that. If x squared is some constants, like, like 4. If you take the derivative of 4, you get 0. So if we treat x like a constant, then taking the derivative of x squared would just amount to 0. Now, if you take the partial of negative xy cubed with respect to y, again, we'll treat this like a constant. And let's think about what is the derivative of y. Well, that's just 3y squared. So there's your partial with respect to y. If I go ahead and distribute that 1/3, I basically get negative 3xy squared over 3. And those 3's would cancel, leaving me with negative xy squared. And now, this is continuous. And what about the partial? Is the partial also continuous? Yes. Negative xy squared is also a continuous function. You can draw it without lifting your pencil. So that's step 1. Step 2, right? So step 2 is to show that this initial value exists on your solution curve. So in terms of the value 1, 6, so I'm trying to choose my words correctly. We have the criteria has been met that there is a solution. That's what this does right here. Now, or I should say, the criteria has been met that it is continuous. So the next criteria is that the point here must be within some rectangle. And the idea is, as you can see, like, you can go back and you can plug this in, right? It exists. So the points for, like, it's continuous for all points, including the initial point in any rectangle, right? So this is in our solution. This is part of our solution as well. It's on our curve. So the criteria has been met for both 1 and 2. In that case, what do we have? So we can make the statement, yes, theorem 1 does apply. That means, yes, there is a solution to this differential equation, and then, yes, again, that solution is unique. It is given this initial point. I'm not going to do example 9 for you, but you should verify to see if you can verify theorem 1 does apply. I'll go ahead and just tell you it does not. It does not apply. But you should, on your own time, you should go through and make sure that you can verify that. But that will conclude. That will conclude our first major section in differential equations, and I'll see you guys in the next video.